stop and start it. Changed, see, that's the higher of the two resistors, so that should be a lower current. Okay, something's not right. Can you X those out, X those guys out, just get rid of them. Yeah, stop. Now let's, okay, good. Now, can you move this down a little bit? Okay, now, put your meters back in. Just make sure they're connected.
I'm looking at copy and paste.
Can you move that guy over? Okay, good. Now, right, see, you have to move the ground down a little bit, it won't hook up to the ground. Same connection. Yeah, you have to delete that line, there you go. Then delete it, start over. Now, don't hook anything else, now set that to, set that to an ambient. Now, let's see what happens. Okay, well, you're reading the same thing, so that's okay. Now go ahead and do this, hooking your side a second. Should get it.
Yeah, it's quite a lot.
Now try. It is weird, maybe something was not hooked up that, anyway, it appeared that you had everything correct, but I got it. Yep. Everybody done? No? Alex, how you doing? Struggling? Let's see what you got. Move those meters out of the way for a second. Okay, so here's, can I just show you something here? So when you hook up an ammeter, you have them connected as you would a voltmeter, taking the reading across the resistor. For an ammeter, you have to hook it up so the current goes directly through the meter itself. So let's I just want to start over here. Show you I'm doing everything you did, sorry. All right, now, we'll do this. And I'm gonna draw a line.
I know.
Like this. Whoops. What I'm gonna do is add a meter. Good. And then I'm going to add another meter. Whoops. And what we're gonna do is we are gonna hook in those meters so that they're part of the circuit. So the current's gonna go through here, gonna come out of that meter, the battery, see that? Forget that little jog there. And then it's gonna, same thing with this guy. So the current goes through the resistor, through the meter, back out of the meter, back to the battery. See that? So that's how you hook up a,
Why are you doing this? You want Vincent? Vincent is a whole iron guy.
that's how you hook up a meter and got a ground. So now when we turn that on, now I don't have the meter up here for the total current, but when we hook that in, connect it to the ammeter, change that to amps or milliamps. 50 milliamps. And same thing for this guy.
I think it's in lighting all of the listeners. Yeah, let's say 2 rounds.
So when I that one's running, that's why. Now I can run this guy. And I've got, okay, so now, yeah, so that's showing the current through, yeah, and it's showing the current through. Now, if you put a third meter here, you'd show the total current, okay? Yeah, it would be right there, looking in through the meter back out again. Okay?
Mr. Coffey, how do you, for measurements for reading the resistance?
The resistance. Okay, what you want to do is get rid of the battery. And then get a meter.
Yeah. Yeah, I know. So I'm just check for a big part of it.
Somehow it just changed the femto. Yeah.
What are you doing? Stop it. Oh my God.
Okay, so what am I, no, keep measuring just these two.
Ohms.
Yeah, so next with the
Parallel resistance, yeah, so now you have to plug that resistor away.
Okay.
Just delete it, or reconnect it.
I like this.
You good, Alex?
Yeah.
You good? Yeah, you have to delete it and start over. Yeah, the only way to do this is to stop the circuit. Now you can delete that. that segment out.
There was a PDF. What is it?
Beautiful, good. You set the meter and see what you get.
It looks the same, every picture said.
Yeah. I put it on milliamps. Yeah, right there. And we can look at it. Okay. Okay, all right, good deal. Okay, I want to show you something. I have here a series circuit, and I've got two 10K resistors, 10 volts. So since the resistors are the same, we're going to see 5 volts dropped here and 5 volts dropped here. Make sense? Simple? Okay. Now, if I had this circuit, and if I asked you to build this circuit, and I said, now I want you to take a meter and measure the voltage across either one of those resistors, let's just say this guy here. So you take your meter and you put the 2 leads there. What's happening is that you are actually creating a series parallel circuit, because that meter, there is a certain amount of internal resistance in this meter. So the very act of measuring the voltage across this resistor changes the circuit. And it doesn't matter, unless you had infinite ohms, you're always going to introduce some amount of error. So let's just say that the resistor, that the internal resistance of this meter is 1 mega ohm. It's huge. So that right there are 2 leads for our meter, and that is, and it has an internal resistance of 1 meg, or 1 times 10 to the 6th ohms. And that's our meter. Let's see how trying to take a measurement affects what is happening in the circuit. Let's see how we've changed the circuit. So what we want to do is calculate the total resistance from these 2 guys in parallel. The 10K resistor plus our meter that we're just trying to use to make measurements of the circuit. So we have an equivalent resistance of R1 plus the meter and R1 times the meter and R1 plus the meter. And that equals 10K times 1 meg over 10K plus 1 meg. Now, all of a sudden, I know that my total resistance is going to be just a little bit less than 10K. All right, so let's see what that actually is. We have 10 times 10 cubed times 1 times 10 to the 6th. Wow, divided by 9,900 ohms, 9,900.99. So that's going to be 9,901 ohms. Let's make sure I got that right. 99, yep, 9,901 ohms. That's the total parallel resistance. So let's do our analysis. We're going to simplify this circuit. So now we have 10 volts, 10K, and we have an equivalent resistance down here of 9901, and that's 10K. And this is 10 volts. So the current is what? 19,901. So let's simplify that even more. V over R. Zero point 50249 amps, milliamps. 50249 milliamps. That's our total current. So that's the current here. And the voltage across this equivalent resistance, this combined resistance of the 10K resistor plus our meter, is now that current times the resistance .975 volts. And that means, so this is, the voltage across here is 4.975 volts. That means the voltage across this guy is 10 minus that, or 5.0248 volts. So you see how we've changed the circuit? On paper, that should be reading 5 volts. But in reality, we're getting, because we've connected that meter, just because we've connected it, we've changed the total resistance. we've connected another resistor in parallel, changed the total resistance, and that affected our reading. But it didn't affect it by much. So the idea is that if you can get the reading to within, I forget what it says in the book, 2 or 3%, then what you have is known as a stiff voltage divider. Let me get the exact percentage here. Oh, doesn't really say. That's interesting. Look on page, in your book, 229. Maybe I'm not seeing it. Oh, here it is.
Stiff voltage divider.
Yeah, it's, so, on page 229. So it puts it in terms of the relative value of the one resistor compared to another. What it says is that when this resistance here, this 1 meg is at least 10 times the value of this, then you have what is known as a stiff voltage divider. In this case, this is 10 to the 4th. 1 times 10 to the 4th. This is 1 times 10 to the 6th. So so this is 100 times the value of the resistor. So this is definitely what we call a stiff voltage divider. If you ever, when you get out into the field and get a job and whatnot, at some point you're going to need a meter. I don't care whether you're mechanical, electrical, whatever. At some point you're going to need a meter. So what you want to do when you buy a really good meter that's going to last for your entire career, make sure that you look for a meter that has the highest possible internal resistance that you can find within your price range. This is like $50, $40, maybe even less than that. I have and I've used this on occasion, but I have a meter at home that I've used for 20 years or so. It cost me $600. It's not a cheap meter, but I'm telling you what, it is a good. It's actually a recording ammeter. I can clip it to a circuit and keep it there for a couple of weeks and see how the voltage changes, see the spikes, see if I'm losing voltage or whatever. And so, yeah, it cost me $600, but because of that meter, I'm able to have a career, So, but anyway, I made it a point when I bought that meter to make sure that it has a high internal resistance, okay? Usually on a meter, that is specified in terms of ohms per volt. Ohms per volt. What you want is a meter that has a relatively high ohms per volt, and you won't know what relatively high is until you get online, do a web search, and compare one meter to the next. And so just within your price range, get a meter that has a very high ohms per volt. Ohms per volt, you won't go wrong, okay? You'll always get some really good measurements, and that's what you want when you're in the field. Okay? So that's what is known as a stiff voltage divider. And the last thing I want to cover tonight is, which is in chapter 6, is the criteria for maximum power transfer in a circuit. And I'll show you something there, go through some calculations. my circuits simple. So, again, I have a series circuit, 10 volt power supply, 50 ohm resistor, and this guy here is a variable resistor. So that's the symbol for a variable resistor. I can change that resistance. And what I want to do is show you how the power that's delivered to this resistor changes when I change the resistance. So this will represent some load that we're connecting up to a circuit, and this would represent, let's say, a power supply circuit. So that's power supply. I have a certain voltage source, internal resistance, and I'm delivering power to a load which I'm representing by a variable resistor. So what I'm going to do is I'm going to calculate the current I'm going to plug in values of resistance here. I'm going to change these values. For each value I'm going to calculate the current, and then I'm going to square it and use power equals I squared R, and then we'll see how much power is dissipated in this resistor as I change the resistance, okay? So the first thing I'm going to do here, I've got some columns. And then the first resistor I want to check is 10 ohms. So if I plug in 10 ohms for that resistor there is 10 ohms. I have a total resistance of 60, and I equals V over R, so that's 10 over 60. So I have 0.166 amps. Square that, and that's 0.0277 amps squared, and the power is I squared times R, which is that times 60, and I get 1.666 watts. Okay? So when that resistor is 10 ohms, it's going to be dissipating 1.666 watts. Let's change it to 25 ohms. So we'll start over. Now I've got 75 ohms total. So my current is 10 divided by 75, or I keep getting these crazy fractions, 0.1333 amps. Square that, 0.01777, and multiply that times I squared R 75, and I get 1.3 watts. Which doesn't seem right. Hang on a second. Let's go back to 10. So I got 10 volts over 60. Oh, okay. Okay. I calculated the total power. So actually, power equals I squared R, I want that number times this value. So that's the power dissipated in this resistor. Now let's do the second one all over again. So we have we have 10 over 75. Well, that's right. That's right. And now I want to multiply this I squared times that. And we get 0.444 watts. Okay, now we go. Now let's go to 40. So we have 10 over 90. And that gives us this current. Square that. Gives us that, and we multiply that current times our variable resistor, and we get 0.4938 watts. So we're increasing the resistance of our variable resistor, and as we do, the power dissipated in that resistor, or the power delivered to that resistor, depending upon how you want to look at it, goes up. All right, so let's make the next one 50. So we have 10 over 100, which is 1/10. Finally, you get a decent fraction. Square that, and that's 0.01. Multiply that times 50. And I get 0.5 watts. Okay, went up just a little bit. All right, let's go to 60 watts. 60 ohms, excuse me. So 10 over 110 gives us 0.0909 amps. Square that. 0.00826 amps. We multiply that times 60, and we get 0.498586. So all of a sudden it went down a little bit. All right. Let's see if that trend continues. I'll make that 75. So we have 10 over 125. And we have, that gives us 0.08 amps. Square that. 0.0064 amps. Multiply that times 75. And we get 0.480 watts. Okay, I'm not going to do any more because I think I've just illustrated what needs to be illustrated, and that is that if you want to deliver the maximum power to a load from a source, let's say you have a 3-stage power supply. So you want to deliver power from the first stage, from the preamp to the intermediate power supply. The output impedance, you'll see this in textbooks, the output impedance, the impedance of that preamp, if it matches the input impedance, if the two are equal, you will deliver maximum power to the load. So right here, when that load resistor here equals the supply resistor, I'm going to deliver maximum power to the load. If I have anything else 40, 25, 10, 60, 75. Some of that power gets reflected back to the source. It's like a wave hitting a wall. You know, it just hits the wall and bounces back out the other direction, if you want a mechanical analogy. But when the two are equal, when the source resistance, I keep saying impedance, the source resistance, we'll get to impedance when we study capacitors. But when the source resistance equals the load resistance, that's when you have maximum power transferred to the load, okay? That's in your textbook. I wanted to illustrate that. It's just stated in the textbook. There's one other thing that's covered in the text, and that's a particular circuit. This is in chapter 6, called a Wheatstone bridge, and it's a series parallel circuit, very specialized contraption used for figuring out the value of an unknown resistor. And I'm not going to ask you any questions on it. I'll just go through it real quick, just so that you know a little bit about what's going on. And the theory behind it. Obviously, if you have an ohm meter and you have a resistor and you don't know the value of the resistor, you just put the ohm meter up against it, right? And that's how you'd measure it. Actually, years ago, because ohm meters are so accurate today, and they have such a high input resistance, you can get the ohm meter, the resistance value of an unknown resistor so accurately that you really don't need a Wheatstone bridge. But years ago, this was the way it was done. And here's the theory behind it. So if you have, let's say you have two resistors in series, and this is 50 ohms, and that's 50 ohms. And you have two more resistors down here. And that's 50, and that's 50. Now current goes through here, through from the battery, it hits that parallel circuit, right? Now that's 50, that's 50, that's 50, that's 50. So you'd think that the current is going to split equally, right? Half of it's going to go this way, and the other half is going to go that way. Makes sense? Well, if it makes sense, then you're right on track, because that's exactly what happens. So half the current goes up here, half the current comes down here, hits this node right here, combines, and then you have the total current there. So it splits it evenly, all right? Well, let's just say you had, instead of 50 ohms up here and 50 ohms there, let's just say you had 100 and 100. You're not going to get an even split. However, let's just say that was 10 volts. Here's what will happen. Across this 50 and that 50, since they're in series, you're going to have 5 volts there and 5 volts there, right? Here, let me redraw that circuit so you can see that a little bit better. Here's what I just drew. So these two circuits are the same. You have the battery, two resistors in series, and on the other leg, 2 resistors in series. These are 50, that's 50, that's 50. This is the starting point. So if that's 10 volts here, I got 10 volts here and 10 volts here. I'm going to have 5 here and 5 here. 5 here and 5 here. Now for this particular case, not only will the voltage split, but the current's going to be the same in each leg, all right? Now what I've done, I'm developing the Wheatstone bridge. Let's say I change these guys to 100s. The current is going to be different. This is 200 ohms total because they're in series. This is 100 ohms total because they're in series. So there's going to be more current through this leg than this leg. But look what happens to the voltage. Absolutely nothing. It still splits. I still have 5 volts here and 5 volts there. All right? Can you see that? Now what if I'm developing the theory behind the Wheatstone bridge? Well, let's just say I changed this to 25 ohms and 75 ohms. And I changed this to, from there to 50 to 150. The voltage will change, but the ratio is still the same. I still have 25% of the voltage will be dropped across here, and 75%, in other words, that'll be 2.5 volts and 7.5 volts, so that the total will be 10. Here it's going to be 5 volts. Here's going to be what, 200? No, it'll be less. Get into a calculator. It's going to be the same because I still have the ratio. This is 25% of the value, 75% of the value. 25% of the 200 and 75% of the 200. So the voltage drop is going to be the same ratio even though the resistors are different, okay? So here's the theory behind the Wheatstone bridge. Let's say you don't know the value of that resistor. That's what you're trying to find. If you know that this resistor very accurately, and if you know this resistor very, very accurately, and you know that ratio is 4 to 1, 3 to 1, 2 to 1, whatever you set it up. If you have this leg and you say, all right, I'm going to establish the value of this resistor, then in order for, when I hit that same ratio, 3 to 1, 4 to 1, 2 to 1, whatever it is, then the voltage here, right there, and right there are going to be equal. And if I put a voltmeter between those 2 points, it's going to be 0 volts because I have the same voltage drop here as I have here, and when I get that resistor matched up, I don't know that resistance, I'm going to make this a variable resistor. When I get that, put in that unknown resistor and vary this guy until I have the same ratio, that voltage across those 2 points is going to be exactly balanced. It's going to be 0. It's like a tug of war going on. And at that point, when I know this ratio and I know the value of this resistor, I can use the same ratio to calculate the value of my unknown resistor. That's the theory of a Wheatstone bridge. like I said, it's very specialized piece of equipment. You don't see them anymore. I think they are still made, but they're not really used that much anymore. But it is based on the theory of a series parallel circuit. It's in the text, and it's kind of an interesting problem when you go through it. I actually have a lab on the Wheatstone Bridge. Maybe we'll do it after the midterm, just so you can see how it works. If we have time, we're going to be getting into capacitors, but I think I might just reach back into the resistor section and have you do that lab. But I'm not going to ask any questions on it in the midterm. So, but it is in the chapter, and I wanted to go over it with you. Okay, who has questions on anything we've covered? Series parallel circuits. We've gone through the equations, we've gone through the analyses, the power, Ohm's law, all that good stuff. And it's just more of the same. Okay, is that it? I'm going to send out an email this week, probably sooner than later, maybe even tomorrow, with a study guide for you to review and look at. And if you have any questions, email them to me, whatever, I'll see what I can do to help you out. Next Tuesday, about the first half hour, we'll have a question and answer session. If there's anything you don't understand, let me know, ask the question, I'll go over the problems before I hand the test out, okay? Yes, Brandon?
How long is the midterm?
You mean in terms of minutes to take?
Go like questions.
Between 20 and 25.
And after that?
After that, what?
No, I was like after that, like.
After the midterm, we're going to be starting in part 2 of the book. Chapter 7 covers motors and generators. We skipped chapter 7. Is that right? Chapter 7 covers motors? Yeah, yeah. So chapter 7 is like the magnetic field and whatnot. We were not going to go over that. That's a different topic altogether. So after the midterm, we're going to be in capacitors, which is chapter 8. And we're going to be getting into energy storage devices, capacitors and inductors. And so some of the equations are the same, but you need to get your thinking cap on for these. I'm going to try to make it as easy as I possibly can. It's just a little bit tougher though. So, all right. Have a good evening, guys.
Do you want this,
Yes, all your labs. Turn all your labs in.
I'm still working on those other labs from the other week.
Oh, okay. Don't forget your homework for the other stuff, the other chapter. I think chapter 5. I know, Nick, you already did yours. Yeah, okay.
What do you want today?
Okay, that's all I know. That's great.
I've written down. I'm going to reset.
I'll keep that in there.
Oh, yeah?
Now what?
So I left it in my note.
Yeah, I had a question on that.
There's 2 lines?
No.
Okay, so
It's the
I
second
turned
one
in the
ignore-
first one?
yeah.
Okay, so I don't need to do that.
No, you're good to go.
Okay, cool, thank you. Yeah, I was like worried.
I was like, well, you got
Alrighty,
the
thanks.
answers to 2 of them.
Sounds good. See ya.
I was like, well, I already got the answers for 2 of them.
Thanks, Alex. Yep, see ya.